In this video, we're going to learn how to measure an angle using radians instead of degrees. We'll compare the two measurements, of course, frequently, but I'm going to assume you're new to this. That's why you're tuning in. So first of all, here's one definition. The radian measure of an angle is calculated by drawing a circle centered at the angle's vertex. And then all you have to do is form a quotient, or in other words, divide the length of the arc that's intercepted by the circle and divide it by this circle's radius. That's the radian measure of the angle. So here we have an angle, and I've drawn not the whole circle. You don't have to draw the whole circle, just the part you need, which is the intercepted arc. And then you'll need two measurements. I did this on Desmo's graphing website and had them measure this for me. They said this arc was 6 centimeters and that this radius for the circle was 4. If you can divide these numbers, then you can come up with the radian measure of this angle. And 6 divided by 4 is 1.5. Notice that the centimeters cancel, so the 1.5 doesn't have any units. You know, when you're talking about these things, you're welcome to say it's an angle of 1.5 radians. But commonly when you write this down, you don't need to put units there at all. So this angle, measured in degrees, is about 86 degrees, and you definitely need this little symbol here. But when we talk about this measurement in radians, we can just write 1.5. Now there's another way to get the radian measure of an angle, and it's better because it's faster and it's easier. What is it? Just draw a smaller circle. Draw something that's called a unit circle. A unit circle is any circle that has a radius of 1. So now, if the arc length, Desmos told me it was 1.5 centimeters, but the radius is 1 centimeter. So what do you get when you divide those? Well, two things. Number one, you come to the realization that you didn't really need to divide, because 1.5 divided by 1 is just 1.5. So in this case, the actual length of the arc itself is the radian measure. The division, though, reminds us that the centimeters cancel and that this radian measurement of that angle is unitless. Okay, so that would be a second definition of how to get the radian measure of an angle. You can pause the video and read it if you want, but I'll just summarize what it says. You have an angle. You want to know its radian measure. Well, superimpose the circle. Make sure that the circle's center lines up with the vertex. Then go measure the intercepted arc. Now, I've got an example here where I do that for a right angle. I think most people know a right angle is an angle with 90 degrees of rotation. Okay? I superimpose a unit circle. I had Desmos measure the arc, and it gave me this decimal, 1.5708. That looks pretty nasty. I'm next going to teach you how to write the length of this arc in terms of pi. Because more often than not, when we're talking about radian measures for angles, people use pi. And how do they get that? All right. Here are 3 unit circles. And for each one, I've highlighted different arcs. Arcs that correspond to all the way around the circle, or 360 degrees of rotation. An arc that corresponds to halfway around the circle, or 180 degrees of rotation, or just a right angle. This arc here corresponds to rotating 90 degrees. So this is 360 degrees. This is 180 degrees. We're talking about the red arc. And this is 90 degrees. Now, how are those measured in radians? Okay, you have to remember a formula from geometry. And the formula is circumference equals 2 pi r. Well, these are all unit circles. So what's the radius? Yeah, the radius is 1. So now the formula looks like 2 times pi times 1. That 1 looks pretty silly now, because 2 times pi times 1 is just 2 pi. That's the circumference of this unit circle. But since we've gone all the way around, that corresponds to 360 degrees. So 360 degrees in radians is 2 pi. What about halfway around a circle? Well, shouldn't that be half of 2 pi? It is. So 180 degrees corresponds to a radian measure of pi. You're going to want to memorize these because they're very important. And then 90 degrees, of course, is half of 180. So shouldn't 90 degrees correspond to something that's half as big as that? It does, and it's called pi over 2, pi divided by 2. I guess we could have done one more. What if we only went 45 degrees and did, I don't know, half of 90? Well, then 45 degrees would correspond to half of pi over 2. That's pi divided by 2 is pi over 4. And you're going to have a lot of these memorized by the time we're done studying trigonometry. Okay, let's see what's next. There's something called standard position. We want to recognize when we're looking at an angle in standard position and when we're not. An 80-degree angle in standard position, I'm going to do this part first. Okay, so what you need is put the vertex of the angle at the origin. Start the angle by running one of its sides, which is a ray, run it down the positive x-axis. And then for a number like 80, a positive number, you've got to go counterclockwise. Do you know what that means? Well, the hands of a clock go around this way, right? That's called clockwise. We're talking about the old analog clocks. Counterclockwise is against the direction of the clock, and that's the way you want to go for an angle of positive 80 degrees. And don't go this far because that's 90. So I'm just making a sketch. I might not have this perfect. But what I did is I rotated in this direction and I rotated positive 80 degrees. And now I have an angle in standard form or standard position. Okay, so how does it go again? Initial side down the positive x-axis. The other side, it's called the terminal side, is here. And it is 80 degrees counterclockwise from the initial side. We'll look at a negative angle in the next example. Now the question is, what's the radian measure? Okay, do you want to draw a little unit circle here? You can. If you draw a little unit circle here, you'd be measuring this arc right here. How long is this arc? And if it's centimeters or something like that, you would just drop it right off. Well, you can set up a proportion. Remember how pi is equal to 180 degrees? Well, this is smaller than pi because 80 is smaller than 180. So one way to do this, if you're comfortable with this, is go, okay, 80 compared to 180 is this arc that I don't know yet, so let's call it x, compared to the radian measure of halfway around the circle, the unit circle. And you could solve that by multiplying these. Okay, don't get too invested in this because I'm going to show you a shortcut in a second here. You can multiply these, and then you could divide both sides by 180. And then you would know what x is. You would know your radian measure equivalent to 80 degrees. Now that looks like this. 80 over 180 times pi, or 80 times pi over 180. But another way to look at it is 80 times pi over 180. And it always comes down to this. It always comes down to this. When you're trying to get from degrees to radians, just multiply by this. That's a shortcut. Should make a certain amount of sense. This is degrees and this is degrees, so those units should cancel. You're going to have an answer now that has pi in it, so it's going to look like a radian measurement because they almost always have pi. So let's go ahead and simplify that. Cancel some zeros, reduce the 8 and the 18 to 4 and 9, and you get 4 pi over 9. We'll do another one of these in a second where I'll just only use the shortcut. I won't form the proportion like we had up here. That's how long this is, 4 pi over 9. And if you wanted a decimal for that, I don't know, it comes out a little bit bigger than 1. Actually, it's pretty close to 1.5, I think. But now we have to do the same thing with a negative 45-degree angle. It has to be in standard position. Our goal is to make a sketch of it, but also to find the radian measurement. All right. Standard position means the initial side of the angle has to go down to the positive x-axis. Then you begin to rotate, and this time you're going to go clockwise because it's negative 45-degree angles. So you'd come down this way until you get halfway to 90, like maybe like this. And then you would draw the terminal side of the angle right through there. There it is, a negative 45-degree angle. And you can label it if you wish. That's in standard position. Now, what is this radian measurement? It's the length of this arc right here. And the shortcut to get it is start with your angle. And if you want radian measurement, multiply by pi over 180. And then just do some reducing. So that's quite literally negative 45 pi over 180. And if you need a calculator to help you with this, just trust me for now. There are 4 of these in there. In other words, 45 times 4 is 180. So this is going to reduce to 1/4. And I'm going to end up getting negative pi over 4. You could write 1 pi over 4. That's not wrong. That's my answer. Now, this is the inverse. They give us an angle. We don't have any diagram or anything this time. They tell us that there's an angle that's got a radian measure of 3 pi over 5. They want us to convert that to degrees. So take 3 pi over 5 and multiply it by, well, instead of pi over 180, flip it over and go like this. And by the way, 180 over pi, these are actually equivalent things. This might not look like it's equal to 1, but it is, just because you're using a different measurement system. Look, pi and 180 are equal. So dividing these makes 1. And believe it or not, all I'm really doing here is multiplying by 1. So that's the idea behind it, but let's just finish up with the mechanics. The pi's cancel, and the degrees take over. So you end up with 3 times 180 divided by 5. You don't need the pi's in there anymore because pi divided by pi is 1. And then 180 divided by 5 is 36, and 36 times 3 is 108 degrees. And that's the answer. We'll get another example of that. Converting 5 pi over 18 to degrees. 5 pi over 18. We're going to multiply by 180 divided by pi. Cancel the pi's. Bring in the degrees. And a shortcut here is that 180 divided by 18 is 10, and 10 times 5 is 50. So that's 50 degrees. What's next? We are to identify, and this is from an online assignment that my students are about to do. And the graphics didn't come through so hot, but I think we'll get by. Identify an angle that's in standard position. There it is again. That's 110 degrees. Okay, first off, I want to show you 2 that are not in standard position. These 2 are not in standard position. Why? Well, you see that little rotational arrow there? Where does it start? It starts from here. So this is where the initial side is for this angle. And it rotates down in this direction. Nothing wrong with that. But this is the problem here. Our initial side is supposed to be on the positive x-axis, not on the y-axis. So similar comment for this one. These are both bad. But these 2 are both good. They're both in standard position. However, this is the one we actually want. Here it is. Here's the answer. Why this one? Because remember, it's positive 110 degrees. And this little red arrow indicates that we are rotating in a counterclockwise direction. If we stopped here, it would be 90, but we've gone 20 degrees beyond that, and that's 110 degrees. Well, then, what is this one? This one's in standard position, but it's rotating from an initial side here to a terminal side there, and that's clockwise, so that's actually negative 110 degrees. So that's not the one you want. You want to go with this one. Now, here's a little chart. Take a look at it. You're going to end up memorizing all these. Or you're going to have a really good way to do these in your head visually. I'll give you a way to think about this, but it's far easier to just start memorizing these equivalencies. They all make sense. For example, here's 60, and here's pi over 3, and here's the image, and we're nowhere near going halfway around the circle, are we? But halfway around the circle is 180 degrees. 60 is only a third of that, because 180 is 60 plus 60 plus 60. Well, that's why I have pi over 3, because I have literally 1/3 of pi. I have pi cut up into 3 parts, and I'm only taking one of those. So that's just one explanation of one of these equivalencies. But we get an example here of doing something like I just showed you. It says, sort of visually find the radian measure of 120 degrees. And if we get stuck, we can look back on our table, because I just showed you this. But no, the visual way to do this is to go, okay, 120. That's not all the way to 180. 180 would be half a circle's worth of rotation. So this is where 180 is, right over here. Well, now you need to know a little bit about arithmetic. See, because you can make 180 by going 60 plus 60 plus 60. Similarly, you can make 120 by going 60 plus 60. So 60 plus 60 plus 60 is 180. We're taking 2 of those. Instead of thinking of these as 60 and 60 and 60, we could think of those as not 180 degrees cut up into 3 parts, but pi cut up into 3 parts. That's right. Here's an arc called pi on a unit circle. It's 3.14159, whatever, right? We're cutting it into 3 parts, so this is quite literally pi over 3. Pi cut into 3 parts. I think it's instructive to call this 1 pi over 3. And then if you take another one of those, you're taking 2 pi over 3. 2 of those pi's that have been cut into 3 equal parts. You could even write this one as 3 pi over 3. Pi's been cut into 3 parts, but now we have all 3 of them. Oh, by the way, we just answered the question. A 120 degree angle has a radian measure of 2 pi over 3. And we're done. Now, identify an angle that's 450 degrees and it must be in standard position. Determine the angle's radian measure. Well, let's get this part out of the way first, okay? 450 degrees, you want to get into radians. What do? You multiply by pi over 180. That way the degrees cancel. And so canceling by dividing by 10 on these, I have 45 pi over 18. That's a pretty good answer there, but both of these are divisible by 3. So you get 15 pi over 6. I think that's the best way to get the radian measure for that. As far as which one of these is that angle in standard position, okay, 450 is 360 plus 90. So that's all the way around the circle once plus another 90 degrees. I'm pretty sure all of these indicate 450 degree angles. But these two are not in standard position. Why? Excuse me. I was looking at the wrong thing. I think this one is in standard position because look at this red spiral. It starts right there, and that indicates that the initial side of this angle is pointing down the x-axis. And let's see, it does go against the clock counterclockwise. Yeah, I apologize for writing no. I think this one's yes. You might want to look at the rest of those to determine why they're not right. For example, this is the one I had in mind. its initial side is here. The rotation starts from here on the y-axis. That's not standard position. And neither is this one. And this one actually rotates clockwise. So that's what negative 450 degrees looks like. Okay, need to make sure I'm still alert here. Find two angles, one positive, one negative, that are, and here's the keyword, coterminal with 70. So the idea is with 70 degrees, you remember we're going counterclockwise, we're going like this, and we're stopping here, and this is called our terminal side. Well, what if instead of stopping there, we went all the way around the circle again, and then another 70 up to here? Look at it again. It'd be 70 plus another full 360 would be an angle that also stops here. It would be coterminal. Figure out what that is. Just add 70 and 360. Add those up and you get 430 degrees. A 430 degree angle looks like this. Go all the way around 360 degrees and then 70 more. Make sense? Now, harder is to go backwards. You could start here at 70 and then reverse direction and go clockwise, backwards, 360 degrees. So to figure out what that is, all you have to do is go 70 minus 360 degrees. I think that's the easiest way to get to it. And that's going to make... I'm looking for it. Well, here's another way to figure it out. I think it's negative 290. You can go negative 90, negative 180. Another 90 is be negative 270, and then you're going to need 20 more. So the answer is negative 290. So that's one negative and one positive angle coterminal with that. All right. Just a couple more here. Find two angles, one positive, one negative, which are coterminal with the angle shown. Oh my gosh, all the answers though are in radians. So the first thing you might want to do would be to convert this to radians. Okay, 315 degrees is 90, 180, 270. So 90 and 90 and 90 is 270 plus 45 more. 45 more. So anytime things come down to 45 degrees, what I like to do is on the unit circle, start cutting things up like this, where each one of these angles is pi over 4. Right? Because I'm taking pi over here and I'm cutting it into 4 equal parts. Here's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Here's 5 pi over 4. Here's 6 pi over 4. And here is 7 pi over 4 is the equivalent of 315 degrees. Now, if you didn't like that demonstration, of course, you can always go like this. You can go 315 times pi over 180 and then deal with all the arithmetic of simplifying that fraction. But it's going to simplify to 7 pi over 4. I was just trying to give you a visual way to figure that out. So what did I do again? Okay, I took this half circle arc on a unit circle that's got a length of pi, and I cut it into fourths. Why did I do that? Maybe I should answer that for you. Well, look back here in this chart. 45 degrees is equivalent to pi over 4. And I explained how 315 was 90, 90, 90, and 45 more. So that's what got me thinking about pi over 4. All right. Now, how do we find two angles coterminal with that? Well, the easy one is to go back this way. You could go negative 45 degrees in the clockwise direction, but that would just be negative pi over 4. I'll show you another way to get that in a second. Another thing you could do is keep with the positive direction, go to 7 pi over 4, and then go all the way around the circle again. And I'll show you two ways to do that. Take 7 pi over 4 and add 2 pi to it. Get a common denominator here, so that's 7 pi over 4 plus 8 pi over 4, and that adds up to 15 pi over 4. That is one positive angle that's coterminal with that. What is that again? Okay, well, it's go all the way to 7 pi over 4, and then go all the way around the circle again. And you get some big improper looking fraction like that. Here's a way to just count it out. Ready? 1 pi over 4, 2 pi over 4, 3, 4, 5, 6, 7 pi over 4. Now I need to go all the way around the circle, and that is 8 more of those pi over 4 parts. So ready? 8 pi over 4, 9 pi over 4, 10 pi over 4, 11 pi over 4, 12 pi over 4, 13 pi over 4, 14 pi over 4, 15 pi over 4. You could just count it out like that. I'm trying to give you different ways to go about this. But I think I like this best. You just have to be able to get a common denominator. All right. Now, we have 2 jobs to do for 2 different diagrams. There's 4 things to do here. Oh my gosh. 1, find the lengths of the minor arcs in these diagrams. There's 2 ways to go about this. One would be calculate the complete circumference of the circle and then reduce it by some fraction of proportionality. What do I mean by that? Well, okay, first of all, how far is it all the way around the circle? That's 2 times pi times r. The radius is 4, and that's 8 pi. 8 pi is the distance all the way around the circle, from M all the way around to M. We clearly don't have that much distance here. Our arc, M to N, is smaller. So one of the things you could do to figure out how big that arc is you could just take some fraction of this, and that fraction would look like this. 45 over 360 times 8 pi. Because 45 compared to all the way around the circle, 360, is this arc compared to the full circumference, which is 8 pi. Now, this reduces to 45 over 360 reduces to 1/8. How do I know that? Well, because 2 of these makes 90, and there's 4 90s in 360. So there's 8 of these in there. Or just get a calculator to figure that out for you. By the way, 1/8 times 8 is just 1. And so we have our first answer. This arc has a length of pi. Now, is that the way I would have done it? No, I don't think so. I would have gone like this. I remember that on a unit circle, not a radius of 4, but a radius of 1, 45 degrees is pi over 4. So that's how big this arc is. This arc has to be 4 times as big as that. Because instead of a radius of 1, you're talking about a radius of 4. So proportional reasoning says, if this radius is 4 times as big as that radius, this arc has to be 4 times as big as that arc. Pi over 4 times 4 is pi. And then I'm supposed to find the sector's areas. I think I'll just give you a formula for that without a lot of explanation. It could be done where I find the area of the circle and then just use that fraction again to reduce it. Yeah, that might be the easiest way to go about this. So let's take the area of the circle. That's pi r squared. Pi r squared in this case, that's pi times 4 squared. That's 16 pi. And then that's the area of the whole circle. But I only have this part of the circle. I want to know the area of this thing that looks like a slice of pie. It's called a sector. Its area's got to be some fraction of the full circle's area. Well, that fraction is this. That fraction is this. So now what you got to do is for the area for the sector is just take 45 over 360 and multiply it by the area of the full circle. Okay, I already explained that this is 1/8. So that's 1/8 of 16 pi. And that ends up making 2 pi. Now, is that reasonable that the area of this would be 2 pi? Yeah. Because why? Well, because you can divide this circle up into 8 equal parts, like this. And each one of these parts is called a sector, and they all have equal areas. And so if this has got area of 2 pi, you got 2 pi, 4 pi, 6 pi, 2, 4, 6, 8, 10, 12, 14, 16 pi. And that matches what we know the full area is. I'm probably over-explaining this stuff. Okay, I'm going to do this one next. This is faster in my opinion because they give you the radian measure. This is one of the advantages of radian measurements. This is a bigger, more open angle than that was. That was 45 degrees. This is 90 degrees. But see, if the radian measure is pi over 2, I know how long this arc is right here. This arc is pi over 2. That's with a radius of 1 on a unit circle. Well, if the radius here is 4 times as big as that, then this arc has to be 4 times as big as that. So the easiest way to figure out that arc is to go 4 times pi over 2, which makes 2 pi. And that's how big that arc is. Notice that it's twice as big as that arc. I mean, these circles have the same radius, 4 and 4. But this was a 45 degree angle, and this is a 90 degree angle. Right? Pi over 2 is 90. So does it make sense that this arc ought to be twice as big as that arc? I think it does, because 90 is twice as big as 45. Okay, I'm going to shortcut the area. We already have some information about the area of this circle. We calculated previously that it was 16 pi. How did I get that? I did pi r squared right here. And I can use that again for this circle because they have the same radius. But now I'm trying to find the area of this sector. Now, does it make sense to you that there's 1, 2, 3, 4 sectors here that all have equal area? Well, then great. Then to get the area of this sector up here, all I have to do is divide this by 4. So area of sector is 16 pi over 4. And that makes 4 pi, which was twice as much area as we had for this sector. This sector area was 2 pi. This one over here is 4 pi. Okay, now if you're interested, let me show you a formula, and then we can get out of here. The area of the sector is 1/2 the angle theta times r squared. What is this? This is a Greek letter from their alphabet. It's often used to represent angles. But provided that this is measured in radians, not degrees, this doesn't work in degrees, you can get areas just by going 1/2 times theta times r squared. Well, I think that's enough for today. It's a little long-winded. I apologize. Hope you learned something. Maybe you enjoyed it. Have a good day.